Good day everyone, my name is Yun and I'm from Group 17 and our topic is Smart Feeding Mirror with Wardrobe Inventory System. Now I'll present the background study of our topic. First of all, let's talk about smart fitting. Smart fitting is a virtual fitting that allows users to view the effect of clothes without having to try it on the clothes physically. Why smart fitting is important? Because of COVID-19 situations in global, it makes customers feel unsafe to shopping and try on the clothes in physical stores, and it has causes a 43.5% of decline in retail sales in Europe. So smart fitting becomes important to help retailers to boost their business. Smart fitting is also very helpful in saving customers from spending hours to change and trying on different clothes. So let's move on to the solution for smart fitting. In 2008, researchers proposed a solution to use multiple cameras to capture different angles of user to do the modeling, and then use another display to show how users look in different clothes. And now researchers propose a more practical way, which is to use a webcam to scan users' body and generate a 360-degree 3D model, and then combine with AR and also machine learning technology to overlay the clothes on user, and user can see the effect on the smart mirror, which the smart mirror can be used as the display and also a normal mirror. Smart fitting also has many advantages in business, such as it reduces the need of display clothes in the store, and smart fitting has many advantages for business as it reduces the needs of display and arrange all the clothes in the store since customers will try it virtually, and it avoids the needs to return items because of misfit. And you also can integrate with recommendation feature, so it can personalize the recommendation for customer and also generate more profit to the business. So our group proposed to integrate smart fitting mirror into wardrobe inventory system to improve users' life quality and also save their time. So next, my groupmate Adrian will further explain the problem statement for our topic.
Good day to our lecturer Dr. Cheng and Ms. Saw. My name is Adrian Shalong and now I will be presenting about the problem statement. The problem statement mainly deals with our inventory management, and as we all know, inventory management is part of our daily lives. Almost every day we have items coming in and out from our household. That said, when a person gets busy, they will most likely to neglect managing their items, and as time goes by, their inventory becomes more disorganized. Some of the problems that are encountered by humans are we will often forget on which clothes have not been worn in a long time. As time goes by, the items in their wardrobe or drawer will be getting more and more, and it will become very difficult in clearing up those unwanted stuff. Next, if users keep their clothes by stacking it in a pile, they will have difficulty in retrieving the bottom layer of the pile because they will have to remove the top layer, only then they can retrieve it. Hence, the solution that we proposes is the smart mirror solution, where aside from the normal mirror function, it will inform the users if their clothes have not been worn in a long time. The mirror can also help users to visualize how would the outfit looks on them without taking any pieces of clothing to try on. This allows users to easily access items that are at the bottom of their stack without removing the top ones. That is all for my part.
Yes, outfit image or clothes image through their mobile device. And this image we store in AWS storage. Next, when user want to use the major mirror, they can choose the images, inventory images from AWS service. Use the major mirror. They can choose the images, inventory images from AWS service and display through the display screen of the magic mirror. The magic mirror is a device that integrates with both real mirror and also half transparency display screen. The user can view themselves with the reflection of the mirror and also choose the option from the inventory. Once user choose their option from the inventory, from the display screen of the mirror. The magic mirror will not capture the images of the user, but instead they will capture the demographic image with the demographic sensor and send the data to AWS service. The AWS service will process the data and return the user coordinates, which accordingly and which will integrate with the image of the code. So the code will finally display to the display screen with the according to the current coordinate of the users. And that's the overall solution of our architectures. If the architecture diagram of our solutions is similar to our previous slides, which show the contribution decisions. Users just use their mobile device and upload their outfit image, and this will integrate with Amplify service, which to deploy our web applications. And these images will store into S3. Once S3 store the images, will trigger the process of recognitions to get the categorizations and also the characteristic of the outfit image and store the result in a table so that we will categorize our outfits in several categories such as blouse, a t-shirt, or its long pants. And next, when user want to choose their image, their outfits, they can choose from a mirror screen which integrate with the display screens, and it connected to top fronts. Once they choose, once the mirror screen is displayed, they will get all the images from the screen, and the user can choose the categories, what shirts they want to wear or what pants they want to wear, and this will also process by a Lambda tool to get the result from the DynamoDB. Once the user choose which outfit they want to wear, it will trigger the tomographic sensors to capture the current coordinate of the user. How does it capture is that they will capture the demographic images and send it to the S3, store it in the S3, and the recognition process will process the image and return the coordinate of the recognized object, store it in the DynamoDB, and this Lambda tool will also get the result from DynamoDB, and this all the coordinate and also the images will apply to the display screens. And that's overall solutions. Next, I'll introduce our AWS solution elements. First is AWS Amplify, which is used to create an Amplify application in the cloud and connect it to the application in the local machine. In our solution, we deploy our web application to allow you to upload their code config image to the virtual world. Second is the Amazon recognition, which is the most important element in our solutions. It does not require us to have advanced knowledge in machine learning, but it can identify objects, label the object, also identify the object coordinates, which using the boundary. The third is the Amazon CloudFront. The Amazon CloudFront, as you can see from previous slides, is connected to the front end of the display screen on the mirror. It's a fast content delivery network CDN service that it can deliver data, videos, applications, and APIs at low latency and high transfer speeds to the user globally. It's also a secure dynamic content delivery and also connection to our device. And the fourth is the Amazon CloudWatch. The Amazon CloudWatch is connected to our recognitions. It's used to monitor the service in analyzing and identifying objects. It also provides us an insight to the action taken in the service, respond to system-wide performance change, optimize resource utilization, and get a unified view of operational. And as I'll pass it the other explanation of AWS solutions to my friend.
Good morning, Dr. Chen and Ms. Saw. This is Ho Jun Sing speaking, and I would like to continue the explanations of our solutions architecture diagram. The part I would like to explain in this diagram is associated with our IoT solutions. It all begins from the thermal sensor, which will establish the connections with the IoT core. And the IoT core will act like a middleman, which will serve the sensor and point the data to the respective AWS services. And in this case, the diagram shows that the IoT core will transmit the thermal images data to an S3 bucket. And when the S3 bucket receives a new object, it will trigger a Lambda functions to process the thermal images and store the variable informations into DynamoDB. And the rest has been presented by my dear fellow teammate. Thank you. Hi, it's me again, and I would like to continue the explanation of our AWS solutions. The first thing I would like to discuss is the IoT Core, which is one of our core services in the system. The IoT Core held responsibility to manage the IoT end devices. Given that the device have the valid certificate and encryption key, the IoT Core will allow the end devices to communicate with other AWS services. The next services is the Simple Storage Solutions, or S3 bucket. It would receive images from the IoT end devices, and it will trigger a Lambda functions with the newly uploaded images to carry out the Lambda operations. When the Lambda functions receive the images from the S3 bucket, it will send the images to the AWS recognitions in exchange for some valuable information, such as if the person is presented in the mirror. And with these informations, it will store them in the DynamoDB. And the DynamoDB will trigger another Lambda functions to carry out another new operations. And the last services that I would like to talk about is the DynamoDB. It is the central place to store all the valuable informations about our thermal sensor and the user informations, and it mostly interact with other Lambda functions to store the processed data. For example, it will store the informations generated by the recognitions which transmitted by the Lambda functions. And thank you. That's all from me.
Good morning, Dr. Chen and Ms. Saw. Today I'd like to present to you the work that I've been done using the IoT Core. So this demonstration will show you how to set up an IoT device using the AWS IoT. So the first thing we're going to do is to select the platform that we would like to work with, and in this case I would go for the Linux platform and Linux.js. So one of the good things about Linux is that it's free license, so we don't need to have any concern about the commercial license or any copyright infringements. And I'm going to provide a name, select next step, and as you can see, every new IoT device will attach a new policy, a policy that allow us to subscribe and publish message. And then there's a certificate. This certificate helps to identify the IoT device, so we can prevent unauthorized access. So the next thing we need to do is to download the connection kit, which I already had, and then we can go to the next step, follows the instructions. So I click done, pause. So what you're seeing here is the code that we extracted from the connection kit. It's not exactly like this. The file was somewhere in here. It's somewhere from here. So that's not what we want to discuss about. What we can discuss about is that the file that's in the connection kits consists of things like the public key, the certificate, the private key. These are the files that we need to verify ourselves to the IoT platforms. So from here, the things we're going to do is quite simple. Once we make a connections with the server, we're going to register our device in the IoT Core. Okay, and we're going to send a message on this particular topic over here. Okay, and the message that we'd like to send is the client ID, which is written here, and then we're going to include the model name, and in this case our model name will be something like Smart Mirror version 1.0. And then we're going to listen on the message. We're going to listen on a particular topic. Okay, and in this case here it says whenever there's a message received from the IoT platform, it will display it out in the console. So as you can see here, we already started the program. Now I'm going to restart it again. You can see we successfully published the registration topics, which is over here. Okay, I'm just going to stop it. Okay. So before we tested our device, AWS actually provided an interactive platform, a test client for us to see whether or not the platform actually receive the message on a particular topics. Okay, so in this case, we're going to listen to this particular topic, and in this case, whichever message received sent by our IoT device that follow this format, which is a thermal sensor, and whatever text that is in between two in the thermal sensor and register, it will capture the message. Okay, so let me show you. Okay, I'm gonna hit enter and publish the topic, and then voila, as you can see, we received the message successfully. Okay, this is the thing that we would like to see. We would like to prove that our device is working. The next thing we're going to do is to integrate another services to the IoT core, to the IoT device. And the things we need is somewhere from here. So we're going to attach a rules to one of our IoT device, and in this case, I'm just going to say testing rules. Okay, and so this is something very similar to SQL query, but in this case, basically what we need here is to select a very specific topic that we can use. So it's very important because this allows us to selectively choose the topic that we want. So in that case, when there's other topics send it to this IoT platform, it will not trigger the rules. It will not proceed with anything. Okay, so we can add the rules, and in this case, I'm going to select send a message to a lambda functions. We're going to see how it works. Okay, and we have some pre-defined functions, lambda functions over here, and in this case, I'm going to go for the IoT registrations. Okay, and add actions. Then we're going to leave this empty, but you might want to add the respective actions for the error handling. And I'm going to say testing. Okay, let's just create new roles. Go to the testing rule again, and we're going to have a quick look to these functions. Okay, we can see if the IoT core has been successfully registered under this lambda. Okay, in this case it does. Okay, it does, and yeah, as you can see here, it attaches to IoT rules. So whichever rules send a message to this lambda functions, it will handle as if they are the same. Okay, and this code, I wrote this code in advance. Basically, this is a code that say, hey, if you receive a message from the IoT core, okay, you can do a pre-check. You can check whether or not the client's IDs already exist in the DynamoDB. If not, we're gonna insert a new items in the DynamoDB. Okay, so let us publish again. So I'm going to send a message again, and and we can see if the lambda actually receive the functions. And in this case, how we're gonna do it? We're gonna check the CloudWatch, okay? Because the CloudWatch will log the information whenever someone trigger the lambda functions. Okay, and in this case, yes, it does. Okay, this is the time. This is the time where we launch the lambda functions, and here the most important part is that the device is already registered. It shows this message because I already used the same client's ID in advance to test whether or not it works. So we're gonna go into here check. Okay, here, and as you can see, this is the client ID that we capture from our IoT device. So basically, what we did here is that we integrate the IoT with the Lambda functions, and from the code, we call the DynamoDB to store the informations that we need. So this is pretty much the thing that I would like to present, and see ya.
Let me start with the demonstration of our system. I will be demonstrating the part of the system where our Amplify application uploads images to an S3 bucket. We will start off in the directory of our React-based Amplify application in our local machine, named close update app. Enter inside the application folder. Here, we can see the installed Amplify dependencies as well as files needed to create a React application. Inside the source folder, there are 3 files that I want to briefly go over. We have our app.js file that contains the main application code, and the index.js as well as the AWS exports.js file, which are important because they help our Amplify application to know specifically which AWS resources are used. The last 2 files mentioned can be improperly configured if the application is not set up properly. First, let's go into the AWS exports.js file. This file is automatically configured when the Amplify application is set up and should not be manually edited because any manual edits will be overwritten when the application is executed. There are 2 points of interest here. First is the AWS Cognito Identity Pool ID, which is from the one created when adding authentication to the application. The second is this line, called AWS User Files S3 bucket, where its value is the bucket name of the bucket imported to the Amplify application when choosing to add storage to our application. Double-check the Cognito Identity Pool ID and the S3 bucket name in this file against the associated values using the AWS console in the event that any authentication issues arise when the application tries to connect to AWS services later on. The next file is the index.js file, which imports the relevant Amplify dependencies and resource values so that our React-based Amplify application can access and use the proper AWS resources. Finally, we go to the app.js file, which contains the main application code for our React application. I will start the application and place it alongside the code for easier comparison. First, we have a button that allows the user to choose a file for upload. Then, when the user decides to upload an image, our application extracts its file name. Next, our application connects to our previously imported S3 bucket to extract the file names of all objects in that S3 bucket. Then, it iterates over all S3 bucket object names and compares them against the file name of the image that we will be uploading. If there is a duplicate S3 object name, the upload will be cancelled and the user will be notified. If the image file name is unique, the application will proceed with the upload of the file to the S3 bucket and notify the user of a successful upload.
Now, let's demonstration on how does the S3 connect to Lambda and trigger the recognitions and return back and get the result back from the recognition. This result will be watched in the Amazon CloudWatch, and there are 2 different recognition process. Is that one is to identify the object upload from the mobile users, which is the up image, and the other is the object upload from the IoT core, which is the demographic image. So now we're showing you how does the recognition of the process will be going through the process. First, I will give a demonstration from S, how it starts from the S3, but I will ignore the IoT call, how the IoT call the image to S3. That is done by the other friends. So now we go to S3 and go to the image. We try to upload an image from my device. So the example will be upload browse image and click upload. So it uploads successfully, and how can I view the result is that I can go to the CloudWatch and go to the log groups. And this is a recognition of this. And this is what the current time. And see the results. And it will categorize it will recognize the coding, and you see what is the character, and you can see what is the character you have saved, loadings, and that is how we identify the objects. And we have like long sleeve, so we categorize it, we get the result and categorize it in our DynamoDB. So the next thing is I'm going to check with the object upload from the demographic sensors. So this is from demographic sensors, and I'm going to do the same things I go to S3 and try to upload the image and see the results. Upload the image and check what is the result. Same thing, I go to CloudWatch for logbooks and recognition process. This is our results. So we're going to find the name of the persons or the label name with these persons and find their current coordinate, which is using the width, height, length, and top. And we know the coordinates. So that's return the results and get back into the lambda. So and this process will pass it to how it set the DynamoDB and get the result from DynamoDB. It will pass it to another friend to explain it.
Good day to our lecturer, Dr. Cheng and Ms. Oh. My name is Adrian Shenlong, and now I'll be presenting about how to create a DynamoDB table, how to create an AWS Lambda function, and how to use the Lambda function to write data into the database. So to create a table, first we click on Create Table, and then we'll create a table name and a table ID. So for table name, we select outfit, and table ID, we'll select outfit ID. And scrolling down, we click on Create Table. And now we have to wait for the status to go into Create Status. Okay, now that the status has turned to active, we click on the table, go to View Items. We can see that our outfit table has been created. And now we'll create a Lambda function. So to create a Lambda function, first we click on Create Function. Next, we set a function name. So in our case, it's set item. And choosing the runtime language. So in our case, we'll just use Node.js, and we'll use an existing permission. And finally, we click on Create Function. And now our function has been created. So next, we'll deploy the code to write data into the DynamoDB. Next, we'll implement the code to write data into the DynamoDB. First, we'll declare the region of DynamoDB that we'll be using. Then we will create a handler to handle the event call that triggers the Lambda function. The Lambda function will take the request ID and use it to set the primary key for the database later. It will then call the setItem function to set the item into the database. For the setItem function, it will take the request ID and set it as the primary key, and these are the data that will be sent to the database. Finally, it will then return a promise back to the handler. And now we'll execute the code and see if it will write the data into the database. First, we'll deploy the code. Next, we'll click on test. It will ask us to create a test event, so we just create a testing. Then all these keys we can remove, and now we'll create. So after this, we click on the test, and the code has been executed successfully. Going back to the DynamoDB, and we click on run, we can see that our data has been inserted into the database. So that is all for my part.
Hi, I'm Gosingyun, and now I'll demonstrate the setup of Lambda 2 to retrieve data from DynamoDB. So first of all, we move to Lambda to create functions, and then we click on Create Functions, and then we choose the default one, and then give a name for our function. Let's name it as readItem. And then we create a new role for our Lambda, and then we click on Create Functions. Then we check on the configuration, click on here, and then we check on the name of the role. And then we go to IAM. So from the IAM management console, we choose the roles and we check on the role name of the function that we created just now. And then we click on it. And then we check the permissions. So because it only has basic execution role, so we need to read data from DynamoDB. So we need to attach policy, and then we search for DynamoDB. So we just fill the full assets, and then we attach the policy, and then we move back to the Lambda functions. So now we modify the code to read items from DB. So now I have modified the code to retrieve data from DynamoDB. So now I've declared AWS variable and also DynamoDB variable, and we also specified the region. And then we will handle the run when the Lambda function is invoked, and then this handler will return the function query code. And then we look at the query code functions, and then this function will return an item from the table outfit with the key and the value that we have defined here. The key, which is the attribute of the item, which is a column in the outfit table, and this is the value of the key. So when we invoke the Lambda, it will return the item with the key and the value that we specified just now. So we test the function, we click on configure test functions, and then we specify the name as test. And then we change the name to testing, and then we delete the value here. Then click on create, and then we click on testing. So the result will be the value of the item that we have queried just now. So now I will move on to the cloud file distribution setup. So first of all, let's move to S3 first. Then we choose the bucket contain the image that we want to display later. And now from the permission, we can see that the bucket is not public accessible, so we want to edit the bucket policy. So we use policy generator, and then we choose on S3 bucket policy, and then for principal we put for all, and then action we want to get the object from the bucket, so we choose get object. And then for the ARN, we copy the bucket ARN and then paste it here. And remember to also add on a slash and also a asterisk. This is to enable other service to access to all the resource in this bucket. And then we generate policy, so we copy it and also paste it here. Then we save change. So now we can see it is already public accessible. Then we go back to CloudFront, and then we create a distribution, and then we choose the origin as the outfit bucket that we enabled to public accessible just now. So we choose don't use ORI because the bucket we already enabled public access just now, and then we click on create distributions, and then it takes several minutes to deploy. So we wait for several minutes for it to deploy. So we can see that it's already successfully deployed for now. And then paste it here, and then we run it. And then we run it, and it will show the image of the clothes. And that's all from our group. Thank you.
My name is Kok Wei Jun, and I'll be now demonstrating an additional feature. This feature allows us to view a virtual reality scene where the color of the entity's or person's clothing changes according to the color of the clothes that the person is currently wearing. First, make sure to use the AWS CLI to correctly configure the correct credentials such as the access key ID and secret access key for the AWS IoT SDK by entering AWS configure in the command prompt to initiate setup. Also, don't forget to install the Python SDK for AWS. Next, we focus our attention to this Python script called random color generator. For every 3 seconds, this Python script randomly generates 3 decimal values. Then it packages them in a JSON object and publishes an update message to the device shadow of our thing registered in AWS IoT called camera thing. Let's open up our camera thing in the cloud and also its device shadow. Let's run the Python script we mentioned earlier. As we can see in the terminal, a new set of RGB values are published in an update message to the device shadow every 4 seconds. Now let's bring Sumerian into the picture. There are 3 things that are needed to link Sumerian to updates of our device shadow state. First is the AWS Cognito Identity Pool ID to authorize communication between Sumerian and AWS IoT. Also, remember to enable the IoT data client. The third important part is the script that we use in the state for a behavior in the scene. In the script, there are 3 parts. The first part gets device shadow values from a thing. The second part parses the JSON device shadow values. And the third part uses those parsed values to set the color of the entity shirt in the Sumerian scene. Let's start the random color generator Python script to see how published messages can change the color of an entity's clothes in the Sumerian scene. As you can see, the Sumerian scene is reacting to real-time updates in the device shadow being published from our local machine.